Alright. So now for some Infinity Battlescape. I'll need to start the game first. So first game capture. Infinity Battlescape. Here we go. Good. So game capture it. Now? Not yet. We'll need some time. I may switch on. There, here we go. I may switch on some video later on. Playing in the side ground, like where is your right? Down here in this direction. On your left screen. Loading the game. Infinity Battlescape. In the last update, we had some new additions. Got mostly, oh, here we go. Mostly guns. New weapons. Actually, it's been waited for quite some while. Also, the new hangar sounds. They are interesting to sound a little bit. Like the center is here, I can hear it. It doesn't move. Somehow weird. Oh, of course. Switch off the missile. And Center Station is still a big battle, so let's go there and see what's going on Center Station. Was increased DPI. That's pretty good. Alright. Closing in on Xantar Station. Yeah. Wasn't fast enough there. Oops. Somehow I'm pretty sloppy lately. I need to just concentrate more on the game. I'll do that now. Alright. Let's close in here. Negative. I modified that sound file of Lavian, the main developer. It sounded kind of weird the first time. I didn't really have a problem with it, but oh, actually we should pick a target. And after that I want to fly some bomber. And I want to disable the HUD and like try to find targets like this. Because I wasn't really able to see the battle until now. I saw some of Space J's clips lately, and I noticed how much better the game looked without the HUD. It's not really. It kind of obstructs the. Is this a enemy or not? Yes. So let's close in on him. Oh, not like this. That's a little bit too much. Actually, I should get out of. Is an enemy? Yes. Let's close in on him. I know I won't hit anything, but it's fun. Ah. Well, that's actually not that bad. Yeah, look at that. I have some major lag here. Like, I clicked the button and there's some major delay. I don't like that synchronization. But, yeah. Well, he's majorly gone. So let's try the missiles. Where did the missiles go? I don't see them. Did I kill him? No, I don't think so. Because those red reticles, they make so much up from... Look, you don't see those ships in the background. You just see them like this. How fast am I moving? I don't know. Oh, there it goes. Now I see the missile. There it goes. And it's gone. I should switch to engine power. Whee! Indeed, a big battle. Big battle. Alright. What should we do? Who should we attack? Let's see. Oh, let's get the HUD back on. Like, this wouldn't be that bad, actually, but... That looks actually quite cool. It looks cool, but it's pretty useless. Like, well, you could... It's actually useful for one thing. So you can like guess what this is. Oops. A little bit too fast there. This guy is fast, that's the thing. They have 2 missiles. We don't have any missiles. We do. Let's see if they hit him. Ah, nice. So I'll switch them off now. Like, this is alright, like, but what now? There's nothing. Ah, actually, I need to press this button, not the other one. Now someone is shooting at me. Like, there could be. Oh, that's a missile. Let's get the normal HUD back on. Look, I just clicked the mouse. Click, click. I click when I say click when I click. Click, 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 click. It's like 200 milliseconds delay. It's really annoying. It's really, he needs to work on that. It's really annoying. Just make the client authoritative on this. It's really annoying, right? Look at this. Look at just the delay in here. I just killed him, didn't even notice. Is there some debug stuff I could open, maybe? Oh, that's not. Ooh. Projectiles. Whoa, that's actually pretty laggy. We don't need the frame graphs. What's the amount of lights now? Just 800. Yeah, and if I get close to the station. $1,700. Yeah, it's 1,000 lights on the station for some reason. Yeah, there are some lights. Those are cool and all. Whoa. Let's stay here, this looks cool. One hit is dead. But the delay is really annoying. What's my ping? 100, 200. Well, it's a lot, quite jittery. Probably because I'm doing quite a lot of stuff. Let's close some of the stuff I've opened. Let's see if this helps. 100, 200. $120, $110. Whoa. Yeesh. Hits? No hits. What am I doing? 500 meters per second. All the ships are purring. Oh, this could work, not the tactic flying nicely in, closing in on this guy. Oh no, I didn't have to do that. 200 meters per second, that's a good speed. Trying to intercept him, getting to intercept course. While all his capitals are fighting. It's actually pretty epic here. Although a bit chaotic. Oh, now he's switching. Who's firing missile at me? Come on. What am I firing even at? This is more than... Get in this fight to fray there. Closing in really fast now on this guy. 500 meters per second. Break. Get it. I'm dead. This is our... Look, I just killed him in one pass. This is the burst damage now. I didn't even hit quite cold, I just sprayed him. And he just died. I didn't see the distance. Let's get this guy. I'm already in his direction. I need to brake even, he's really fast. But not in my direction actually. Line. Oh, too fast. So, I shouldn't chase him. Ah, I could chase him. Brake. And dead. Next one. Oh, that's actually... is this... Yeah, that's where is he flying? Really fast. Nah, I shouldn't chase him. Get this guy. And I'm out. Need to recharge. Oh, come on. Oh, I need to boost to run away. You missed, missile. Let's find a new target. Okay, it's also flying at 500 meters per second. You're missing! How about some better aiming? Whoever... yeah, well, I'm not that much better. Look at those guys, look at them. Is he even aiming at him? Don't know. Someone hit me. Huge chance. Quite erratic moment. 2 hits. And that. Ouch. This guy's hitting me. I'm dying. What? I'm not dead? I'm dead. Pretty much dead. Something's off. My cooling system, something's off. Ship is spinning up, but it doesn't. Let me check for a second. Where's my key? my key to get into the computer. What else don't want to spin up? The sensor either has fallen out or another spin up. Need to check the code again. How many misses do we have on this thing? 18. Yeah, let's have some fun with those. Oh no. I didn't watch. Did not watch. No. Did not watch the screen. That's what I get for it. Doing that. I really like the new. These colors are great for Cinder. And also don't set standard warp settings are just stupid. Yeah, like this. Now I can just push forward. What's that? Wait, this looks cool. Let's get down there. This looks kind of cool. Volcanic rock coming out of the desert. How large is this rock? It's pretty large. Of course it is. Let's switch like that. Oh, it's actually not that big of a rock. Not that high. Just 2 kilometers or something. Still a pretty big mountain. Yeah. Looks like 2 kilometers. Well, yeah, that's what I get for. Let's push out of here. Bend our missiles and then. Out and away. Here we go. Once out of the atmosphere, we can go quite fast. Oh, there's a giant station. We'll later go down to the surface and to the base there. You can actually see the base from here. It's back here. Pretty good visible from space. How far away are we actually? 400 kilometers, that's alright. Get back to the normal hut and let's like... Let's kill a few bugs. This is really cool. Just blasting them. Who's killing me? Explosions. Yeah. What's your problem? Did I hit it? No, it hit me. Ah, chance. Let's kill those guys. Oh, he actually killed me. Everyone was shooting at me. Did we make our money back? I think we did. How much is it? It's 30. It's pretty cheap. The fly back to the battlefield, to the Battlescape. Accelerate to 10 million meters per second. Brake. Let's go to engines. This to make should like switch power modes more frequently. Switch to weapons. Brake. Switch to engines. Brake. Get in range. That's a lot of NPCs. I have the feeling this is more NPCs than before. They fly much more closer now. That's definitely fixed. Weapons. Disengage. Too far away. Is it 1.5? It's 1. Alright, he's going away. Let's send some presents. He's dead. You don't even have to look at him. You don't look at the fight, you just kill them. Whoa, what's this? Something big. Oh, the ship is targeting me. Whoa, did I just fly through the... I need to GTFO. Target these guys. Yeah, coming in hot. Where are you aiming to? Shouldn't you aim like in one direction? Like this. What is this supposed to be? .500 meters per second. They fly so fast. Why? They don't need to get fast somewhere. Where's this guy going? He's dead, yeah. Everyone's shooting with blaster guns. Look at that. Fire missiles! God damn it. Ah. It was a destroyer again. Go, 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 go. Overcharge the engines for the win. Oh, god damn it. Oops. We're not in the atmosphere, so that's... Need the new space world geometry. Break. Also, really annoying the standard setting. The warp. I really don't like where all the fighters are fighting, like in between those. Oh, it's close to the carriers, right? That's like supposed to be like this. This is just one. Where's the rest? This is a good target. Let's get him. Why is he flying at 1 kilometer a second? Oh, really? Let's just kill him. Let's see if the missiles can get him. .2 kilometers a second. But in our direction, so let's see. What? Friendly fire? Oh, there are my missiles. No! Oh, God damn it. Let's get another kill. Okay, we're dead. 12 kilometers. Nice, that was a nice one. Really close. Fucking shaking, I can't see anything. That head. Okay, I'm closing in not fast enough now. Look at that shaking, that's no way I can hit anything at this distance. Now, here we go. We're getting closer now. Something shooting us. We don't have any missiles more, but we have some torpedoes. Let's like try to launch them. There's one guy here. Oh, one right here. That's a little bit easier. Let's try this. Yeah, nice. Fire! Reload! Oh. What is going on? Objects in view screen may appear closer than they are. may appear farther away than they are. Wow, this guy's getting devastated. Ah! Which one is setting for me? This one? This one? This one? This one? I want to shoot one down. But let's see it. This one is it? It's this one. Let's try to get it. Weapons. Counter weapons. Yes! Actually, I think it hit me. I lost shields. Let's go to the station and watch Isaac Arthur's video while cruising a little.
Many people commute as much as 100 kilometers to work every day. Interestingly, this is also about how far it is to low orbit. If we ever want to have a truly serious presence in space, we are going to need a lot of infrastructure in orbit. Today, we are going to try painting a picture of what that would be like, and review some of the challenges we have to overcome to achieve it. Many of those challenges get far easier as you get more and more infrastructure built up there, but one, the danger of orbital debris, increases as you get more potential sources of debris in orbit. You can have a runaway chain reaction of destruction we'll discuss later today known as Kessler syndrome, which has the potential to cut you off from space altogether. So how do we start building up that infrastructure, and what should it be? There are many approaches, and since last time in the series we discussed spaceports in terms of the Gateway Foundation design, I thought we'd just pick up from there. This concept of building in space is hardly new, but in recent years there has been an increasing focus on the use of robots and drones for doing the work, so we'll spend some time on that too. Whether new plans or old, what they all seem to have in common is a big problem of what exactly you are manufacturing up there, and what the infrastructure and factories would be for. As I mentioned in the interplanetary trade episode, in the long term, Earth really has nothing it needs to import besides precious minerals like gold and platinum and rare earth elements, and Earth's obvious exports are people and information. The latter doesn't require much infrastructure in space. Earth churns out endless volumes of science, movies, TV shows, etc., and can export them by simple radio or laser broadcast. I made those statements in the context of interplanetary trade, and in doing so, I lumped Earth's space-based industries in near-Earth orbit with ground-based manufacture. Instead, today, we will separate the industries on Earth from those in orbit around Earth. We actually don't need much infrastructure to receive precious metals from asteroid mining. It takes a lot of fuel to move materials at interplanetary speeds, so by and large, you do your refining on location and send it to Earth in a pod to aerobrake in our atmosphere and be picked up by a ship. You wouldn't send it to Earth orbit for smelting and transport it down. However, the value of refined metals like aluminum and steel in LEO cannot be overstated. The budding space construction industry created by a project like building a spaceport will be very hungry for raw material inputs, and launching all of them from Earth is expensive. Many folks will be aware of the recent successful Falcon Heavy launch that put Elon Musk's Tesla into a solar orbit that will pass by Mars. I have to admire the publicity stunt of that launch. especially the inclusion of The Hitchhiker's Guide to the Galaxy by Douglas Adams in the glove box, as well as a towel and a sign saying "Don't panic," and of course, the data storage device with Isaac Asimov's classic space trilogy on it. Importantly for our purposes today though, the Falcon Heavy will allow us to put payloads of up to 64 metric tons, a mass greater than a 737 jetliner loaded with passengers, crew, luggage, and fuel, into low Earth orbit in a single launch. It is the most powerful operational rocket by far, and it can deliver more than 2.5 times the payload that the space shuttles could. We could actually carry the million-pound mass required to recreate the entire International Space Station in only 7 launches of the Falcon Heavy. We haven't seen something that powerful since the Saturn V rockets last flew astronauts to the moon in the early 1970s. Unlike the Saturn V rockets, though, the Falcon Heavy is reusable, and that should significantly lower the cost of launching materials into space. SpaceX aims to have up to 2 launches a day. That's not to say it will be cheap, but it will mean we can more cheaply bootstrap a space-based industry from Earth to start mining the materials we need in space from asteroids and the moon. Orbital infrastructure to accommodate those activities would mostly be places like our spaceport for processing all the people coming and going. For other infrastructure, we have to ask, what would you actually benefit from building in space? What products are better built there rather than on Earth, or in situ on whatever planet, moon, or asteroid that either needs them or extracts the raw materials for them? Not to mention the things that can be done in space or zero-G which can't be done here on Earth. To manufacture anything up in space implies that it has some advantage over doing it on Earth first, then shipping it to space. That could be something like a large spaceship or station that couldn't be built on Earth and shipped up, 100-meter plus telescopes, or something like a water recycling plant, because it's cheaper to recycle water than import it up from Earth. Similarly, for anything wanted far from Earth, like asteroid mining equipment, being able to make it near Earth but not having to drag it out of our full gravity well is quite advantageous. However, there are features of space that are beneficial to some manufacturing. Solar power is vastly more reliable in space, where there are never any clouds and where nighttime is very short. The higher your orbit, the less of it is in Earth's shadow, and while low-orbit satellites spend a lot of time in Earth's shadow, it's still less than an hour, not many hours of twilight and night like on Earth, meaning you don't need as much battery capacity. Similarly, microgravity has significant manufacturing advantages. There's no pressure in the hard vacuum of space either, so many materials typically go straight from solid to gas, and there are some manufacturing techniques that use vacuum and would use them more if getting a near-perfect vacuum wasn't such a pain as it is here on Earth. One example is solar panel manufacture, which often includes a step that needs to be done in a vacuum, and this is an expensive part of the process to achieve here on Earth. Many crystals form best in microgravity too, and those have applications in industries like medicine, optics, and electronics. Another technique that is much easier in microgravity is microencapsulation, which has applications in adhesives, anti-corrosive coatings, pharmaceuticals, self-healing coatings, DNA protection from degradation, and sample storage. Interestingly, many of these applications will not only be useful as export products back to Earth, but will also be very useful to the space infrastructure itself. We are already aware, though, of a technology that we can only make in high quality and quantities in microgravity that will be the next iteration in fiber optics and lasers. These are called heavy metal fluoride glasses, the best known of which is a family called Z-blands, named using the first letters of the chemical symbols for the metal atoms that they are composed of: zirconium, barium, lanthanum, aluminum, and sodium. That last one has the chemical symbol Na, so that's where the N comes from. They may make the silica-based fiber optics we are currently using look like a horse and cart compared to the sports cars of the Z-blands. They would solve many of today's problems we have in spectroscopy, sensing, laser power delivery, and fiber lasers, and amplifiers. Given that they also have military applications, there is a strong economic and political push to manufacture these. On Earth, Z-blands are difficult to make in high quality because gravity causes the formation of crystals in the structure, and these crystals disrupt its desirable optical characteristics. Doing this manufacturing in microgravity avoids this problem because crystal formation is all but eliminated. A kilometer run of Z-band fiber optic cable was 3D printed on the International Space Station last year, and this was returned to Earth last month. We will probably hear more about that industrial experiment in the coming months. The importance of this experiment is that it is arguably the first one to test true industrialization in space, and this shows that we are on the cusp of our move into space industrialization. We are only at the beginning of our understanding of how to do space-based chemistry and how we can perform industrial processes in a vacuum and microgravity, but based on results so far, there will be many more useful and innovative processes and products that can be produced more easily in space than down on Earth. Now, I noted at the beginning that orbital space isn't much further than many folks commute daily, and as we saw in the Orbital Rings episode, it is possible to get huge amounts of people and material up to space fast and cheap enough for daily commutes. But more importantly, the actual commute time to low orbit is about 1 millisecond. That's because you don't have to have equipment being run in orbit by people on site, and unlike robots sent to other planets and asteroids, they don't have to be smart either. They just need to be something a human can decently control by remote. So you don't even have to commute to work, you just log in at home, and even time lag when the drone is on the other side of the planet is short enough you'd barely be able to notice. However, if your robot has even a small amount of AI built into it, one person might be able to control mini drones, bots, or PODs, performing the most simple to complex tasks. This addition of AI also makes large-scale unmanned robotic missions much more viable than they are today, because an AI can compensate for communications lag. Needless to say, we don't have many drones and interfaces quite up to that quality yet, but when it comes to telepresence surgery, we have been doing that since the Lindbergh operation back in 2001, when a surgeon remotely removed a patient's gallbladder. The surgeon was in New York, directly controlling a robot operating on a patient in France. Nearly 2 decades later, many other examples of this telepresence surgery have been performed, but it is still not the norm because the need for it is marginal, meaning it is not widespread or cost-effective. Having said that though, the technology is proven and available for when we need it. Also, needless to say, that would alter a lot of Earth-based mining and manufacturing too. Even ignoring manufacturing dangers, we have a lot of factories that would benefit from being remotely operated in conditions that are rough on humans. A pretty big chunk of infrastructure in space is going to be centered around humans, again why we began our look at this concept last time with spaceports, and why we probably see a surprising amount of space-based hotels or even private homes. It's not something we tend to think about much, but your big issue with a private home in space is the size needed to supply decent artificial gravity by spin, and that can be gotten around by having many such homes on the ends of tethers like pods on a carousel wheel. On top of those, we have 4 major subcategories of early infrastructure we'd expect to see. The first is power generation. As I said, solar is more reliable in space, and also very easy to beam around. You can have panels on a given installation, but you can also beam it from more specialized power collectors, as they don't need to worry about the atmosphere getting in the way, and keeping a beam on target and focused to a spot a few hundred or 1,000 kilometers away in space is pretty simple. However, we can also beam that power down and out. The down part is familiar. Instead of using up useful space down on Earth, you collect power up in space and beam it down in concentrated fashion to collectors on Earth. Likely, you'd use several collectors as satellites move around the planet and can redivert the beam if you've got problems from clouds or breakdown or whatever. The beaming out part is a little less familiar, though we've talked about that before here, and the new Project Starshot has helped familiarize folks with it too. You can push things with light, up to truly high speeds, like the laser highway we've discussed, but you can also heat or power things with such beams, and that's handy for spaceships too. The notion of an ion drive is one that accelerates slowly but to a very high speed, by pushing propellant particles out at very high speed, and that's very appealing for interplanetary travel or moving around things already in orbit where you don't need a high thrust, just a long, slow, and steady one. It still takes fuel though, both for the propellant and whatever is giving it the energy to heat that propellant up. And it's common to want to run an ion drive either on a nuclear reactor, which has a fair amount of problems attached to its use, or on solar, which isn't terribly dense, particularly as you get further from the sun, and means a ton of panels you have to drag along and protect from micrometeors. A beam going to a ship though, be it a ship or a satellite in orbit or something moving between planets, can provide the energy to superheat that propellant, saving you a lot of mass. And this actually works even if you are trying to approach the beam, which is shoving on you, because the beam carries less momentum than the propellant it will energize does, and while some materials are better than others, you can pretty much use anything as that propellant if you have to. A large percentage of the energy an ion drive uses is for ionizing that propellant, some being much lower energy to do, so if your power is coming from an external source, you can consider propellants that are easier to obtain economically or in an emergency. Short of us developing a viable commercial fusion reactor, solar power in space is going to be a huge chunk of the orbital infrastructure. Indeed, it might be preferable over fusion in many cases, to power things in orbit, to send power down to Earth, to beam power out to ships or installations far from Earth. It also has the dual advantage of being handy for vaporizing space junk and meteors or giving them a shove. Of course, it is a little problematic in that you can also vaporize things down on Earth, so you want to design all such beams to have a maximum focus spot that can't blow things up fast down on the planet, or for ones where we need a tight focus, like for hitting distant spaceships, use those frequencies of the spectrum that are most disrupted by our atmosphere, or use enhanced adaptive optics to jumble the spectra when not pointing exactly where desired. Such solar arrays would be a huge chunk of the orbital infrastructure, but look like an even bigger portion as they generally be slim and wide. Now, you might be thinking that if we did enough of them, they might block sufficient light getting to the planet. But you would need a lot of those, and you can also place them in higher orbits where they get blocked by the Earth's shadow less anyway, and you can always have them with a counterweight so they can tilt on their axis when directly between the sun and the Earth to let the light pass uninterrupted. Though you might not want to. A problem every technological civilization is likely to face is their planet getting hotter, not just from greenhouse gases but by sheer energy needs. A few hundred terawatts of fusion power might be totally carbon neutral, but it still puts out heat. So you might actually want to introduce solar shades to block some of that light, or some of its less useful frequencies like infrared, from hitting Earth. A millimeter-thick chunk of aluminum foil as big as a football field would not be big enough to be seen obstructing sunlight to us on the ground, is pretty cheap per unit of area, and could presumably be mass manufactured up there far more easily than anything else, meter for meter. They are also fairly immune to micrometeor damage for much the same reason it's hard to destroy a sheet on a clothesline with a pistol. The bullet goes straight through without really doing functional damage. Done properly, you get a mirror, with which you can bounce light into a close collector dish, which can then spit that radiation out as power too. A solar panel doesn't have to be as wide as all the light it collects if it's got a mirror and a dish concentrating that light for it instead. So you can handle concerns about a warming planet while increasing your power supply for beaming down to the planet, using up there or beaming off to distant objects. These same kinds of giant mirrors can be used for huge telescopes too, though you'd want to ratchet up the quality of the mirrors a lot. I want to save ridiculously big telescopes for its own episode down the road, but once you are up in space, building in space, you can make things that make the Hubble telescope look like something you'd buy in a toy store, and able to directly image exoplanets. Indeed, you can make planet-sized telescopes thinner than paper. Again, something we'll discuss another day. Another big part of that early infrastructure is going to be fueling stations. As I said last time, you can predict a lot of things you'd want on or near a spaceport by looking at what we keep near airports, seaports, train stations, and truck stops here on Earth. You'd expect to see these as parts of spaceports, but you might prefer to keep your fuel in the same orbit, but a couple kilometers forward or behind, and anything automated, be it automated spaceships or just satellites with fuel for station keeping, have no need to dock at a full-blown spaceport unless they need hands-on maintenance. They wouldn't necessarily need to dock either. Those fuel depots might have bots that could fly out with fuel to them directly, then come back. You also don't necessarily need fuel for station keeping either. You could shove them around with beams, but we also have the electrodynamic tethering approach we discussed in the Skyhooks episode, whereby using a long tether with power running through it, we can magnetically push off Earth's magnetosphere. All of which means you've got an awful lot of stuff in space. Not just ships and stations, but huge solar arrays and long tethers. The space is big, really big. Even just around Earth, it is hard to believe how vastly, hugely, mind-bogglingly big it is. However, that stuff in orbit is spinning around the planet several hundred times faster than a car on the highway, and so each bit covers a lot of ground, and even a very tiny bit can smash into things with all the kinetic energy of a car on the highway. That screwdriver you lost working on the outside of a space station that floated away at walking speed can slam into another orbiting object on a different trajectory like a cannon shot, and in the process throw out more debris that scatters everywhere, smacking into more things, which shoots out more debris, and so on. We see an example of this in the film Gravity. If you've got a lot of material in orbit, it's potentially possible for a single small piece of trash to set off an apocalypse in orbit. Down on the ground too, since a lot of bigger items we might put up there could have bits and pieces fall down big enough to survive re-entry and leave a crater somewhere, possibly someone's home. So even infrastructure on Earth probably wouldn't survive unscathed, but up in orbit, you could potentially have a total wipeout of all your equipment and personnel. To make this worse, while a lot of that scattered debris would fall down and burn up, a lot of it would persist in orbit for potentially many years. This collision cascade, or ablation cascade effect, is also known as Kessler syndrome, for Donald Kessler, who noticed the possibility in 1978. 40 years later, it's still a serious concern. Right now, there are a couple thousand satellites in orbit, and nearly 1 million pieces of space junk a centimeter across or larger floating around. That junk kills about 1 satellite a year. The more objects you add, the higher the probability of a strike, and the higher the number of secondary debris you get from that collision. At a certain density, you can get a feedback runaway process that ends in everything up there being obliterated. When it's over, everything is wrecked, and you can't put anything new up for a long time, as all that debris is still up there. Low orbit, the place we most like to put stuff and have to pass through to get to the higher orbits, would have the most initial debris, but also the shortest dwell time, as the very thin atmosphere up there causes enough drag to slowly deorbit debris to burn up in the atmosphere. The higher you go, the thinner that is, and the longer it lasts, potentially persisting millennia in the higher orbits. You can't launch through that. It would be like jogging through a minefield. So until it clears out, either naturally, which could take generations, or artificially, your planet is grounded. Nobody is going anywhere. Now, if this happens, there are some approaches we can take to speed up clearance of debris. You can also potentially armor your spaceships up like tanks, but needless to say, that takes a lot of mass, something that's always to be avoided with spaceships, especially ground-to-space varieties as opposed to space-to-space. However, ideally, you want to be able to stop the cascade before that domino effect begins. There's many ways to do this, either clearing it afterward or stopping it before the runaway. Figuring out the best approach based on your technology is going to be a high priority for any spacefaring civilization, be it us in 20 years or some Kardashev 2 civilization building a Dyson swarm, for which Kessler syndrome at a solar system-wide scale would be absolutely terrifying. This starts with detection. You have to start by figuring out what the minimum size is that you need to intercept, based on your standard shielding and armor, and how much pounding your paper-thin solar shades can absorb. Now in space, you can use pretty much any wavelength you want for radar, so you want something most material is going to reflect, and has a wavelength smaller than that minimum size you need to intercept. Then you need to flood orbital space with that wavelength with a ton of emitters and receivers picking up every little fragment. As I mentioned, there are quite a few ways to deal with space junk, but one of the preferred ones proposed is called a laser broom, and this can be deployed in space or from the ground if you are cleaning up the mess afterwards. A powerful laser could flat out vaporize the debris, but the laser broom just heats one side of the object up. This causes ablation, where the material evaporates a bit, which produces a little thrust, knocking the material out of its current somewhat stable orbit into one which decays faster. That's a good way to deal with a cloud of debris post-runaway collisions, but you can also use it to nudge a bit of debris on a collision vector with an object, preventing the runaway effect in the first place. By embiggening the laser, we could provide a bigger shove or outright vaporize it. It's not a good and efficient approach when you have a ton of debris, but good for stopping that from happening in the first place, and another reason to have lots of power collectors and power beaming stations in space. It's also a good reason to include point defense systems on a station. Other approaches for mass clearance would include everything from shooting the debris with aerogel bullets to deorbit them, or launching a big nuke up to explode and clear a sector right before a ship passes through. But ultimately, we want to prevent that cascade from ever starting. The general approach would be to recycle everything you can, blow what you can't into a fast decaying orbit to burn up, tether every piece of external equipment and tool to the ship or station, and have little drones to run off and grab things that get lost. One of the Gateway Foundation designs is just that, the Errant Object Retrieval Program, or EOR. The current design for the ISS has an observer drone that heads over to an active work area when an EVA begins, and is packed full of object recognition software and knows to look for telltales of lost gear, like when it begins spinning around its own center of mass. There's no air in space, so stuff almost always tumbles when it gets loose. Later generations of observer drones in many different sizes will see extensive use in space construction, offering numerous viewpoints to construction control. Small observers will get in tight to inspect welding, and big ones will survey the whole worksite. The second part of that is the amusing but aptly named Frog's Tongue drone, because it roams around the station hall with the EVA astronaut and extends an armature to nab loose gear. This wily but versatile drone will later become the mule that carries astronaut tools and parts in toolboxes to a worksite. Right now, an astronaut has all this gear attached to their spacesuits, very cumbersome. The last of this trio is the retriever drone, which has its own jets for chasing after something that's gotten out of range of the Frog's Tongue lash, be it lost gear or even an astronaut. These specific designs are intended for the current ISS, but represent the basic concept of drone we will want with all our orbital infrastructure to minimize space junk, and of course with more sophistication, they could form automated repair for smaller installations, either remote controlled or via AI. As we do get more construction up there, we will need to worry about entire structural segments getting lost too, if we are talking about a piece of truss like from Tether's Unlimited Spiderfab and Trusslator, or Gateway's segment assembly line. You don't want a big truss whirling through orbital space. Those don't even need to be going orbital speeds to ruin your day, and you need to be looking at a large detection and retrieval or elimination system spanning orbital space if you are doing a lot of construction and manufacturing in orbit. With space manufacture though, we are worried about more than just lost or broken tools and equipment causing debris. We also have to worry about space pollution. The problem is that if we allow, say, water to escape, it could freeze into hypersonic deadly hail. The same is true of welded metals. The technology needed to capture that debris at source is probably relatively simple but has yet to be tested, and it is probably well past time that we got going on preventing this type of problem before it gets to Kessler syndrome levels. Another option is to reuse your old infrastructure by recycling it. 3D printing will form a big part of space infrastructure for several reasons. Firstly, it is easier and considerably cheaper to ship a printer and the raw materials up into space and have it print parts on demand than it is to ship up every conceivable item you might need. Secondly, and more importantly from a Kessler syndrome point of view, 3D printing materials generally allow them to be recycled. This is being taken seriously by various space agencies and is actually being tested early this year. The Refabricator experiment is a 3D printing experiment scheduled for imminent launch to the International Space Station. It will process plastic feedstock through multiple printing and recycling cycles to evaluate how many times the plastic materials can be reused in the microgravity environment before their polymers degrade to unacceptable levels. Skip on any of these preventative measures, and your very expensive and valuable orbital infrastructure could go crashing and burning down into the atmosphere. Needless to say, intentionally spraying a planet's orbit with a billion pea-sized metal spheres is a pretty good way to cripple their orbital infrastructure and defenses, something we will talk about more when we get to planetary invasions later this year, in continuance of our series on space warfare. First though, we will look at interstellar warfare next week, and contemplate how you might actually go about fighting engagements that could take centuries, and some of the overtop weapon systems Kardashev II civilizations might employ against each other. The week after that, we will contemplate the end of civilization when our planet and sun die, and how to avoid it, in Civilizations at the End of Time, Dying Earth. And the week after that, we will contemplate circumventing space travel entirely with teleportation, and ask if such a technology could ever exist, and how we might do it. We'll also look at some creative approaches and examples of its use in fiction, such as our book of the month, Richard K. Morgan's novel, Altered Carbon. For alerts when those and other episodes come out, make sure to subscribe to the channel. I also want to thank the Gateway Foundation and Orbital Assembly for their help with this episode and the last one in the series on spaceports. They have a Kickstarter for their drone development just starting up, and are looking for volunteers to help on their projects, so if you'd like to contribute some funds or time to help them out, or just learn more, I'll include a link to that in the episode description below. If you enjoyed this episode, hit the like button and share it with others. You can also join us at our Facebook or Reddit groups, Science and Futurism with Isaac Arthur, to discuss these topics more. Until next time, this is Isaac Arthur saying thanks for watching and have a great week.
Make sure to subscribe to Isaac Arthur if you liked that episode. Hey, he does some cool video essay kind of stuff. Really interesting. Well, I'm going to chill some more out. Have a good time, whoever's watching, if someone's watching. Ah, god damn it. What? That didn't kill me. Well. Now here we go. Haha. Goodbye.